Hello everyone, welcome back. This is Sushma. In this video, I will share how we can deal with ordinal data when fitting a regression model. In research, we often deal with ordinal data. These are the data that have a natural, meaningful order in them. For example, income level, if that has been presented, is a low income, medium income, and high income. So here there is a natural order, right? Because low is less than medium and medium is less than high. And even though we don't know what is the exact difference between these two levels, but we know that one level is in higher rank than the other. So other examples would be some data that is presented in a Likert scale, like strongly agree, agree, neutral, disagree, strongly disagree, or something that is presented as a pain score, and many others. And the question is, when fitting a regression model, do we treat this data as a continuous data, or do we treat this as a categorical data? Fortunately, we don't have to guess. There is a test that can help us make that decision. So I will show that here using an example how we can make that decision using our statistical analysis. So let me walk you through that. So in my RStudio here, I have loaded the required packages in the first step here, and secondly I have loaded my data. That data is a hospital visit data saved as a CSV. So I read in the data, and when we open that data, we can see there are three different variables: hospital visit in past year, which is the outcome variable, and then education and age. So hospital visit is recorded as a numeric variable, and education and age, all of them are recorded as numeric variable. So our question now is, do we treat this second variable education here as it is a numeric continuous variable, or do we treat it as a categorical variable? So to treat that as a categorical variable, we will need some indicator variable, right? So we can create those indicator variable using muted function here. So I have done that using that function here. And the first indicator variable I created is education underscore low, which will be recorded as 1 if the education variable has 1 in it. Otherwise it will be 0. Likewise, the second variable is education medium, which will be entered as 1 if education is entered as 2. Otherwise that variable will be entered as 0. And the third variable is education high, which will be entered as 1 if education is equal to 3, otherwise 0. So let me run it. And when we run it, now we have 6 variables, and let's see how that looks. So here we have these 3 different indicator variables for education variable created. Now let's fit our linear regression model. So the first scenario will be treating it as continuous, treating education as a continuous variable. So let's assign a name, model 1, and let's fit a linear model where our outcome is hospital visit last year. Then we will keep the education variable, and then let's also include is in our model, and our data, specify the data is named as this data here. So let's run this model, and now let's check the summary. Model 1, and when we run it, we can see the summary for model 1. So here we can see that there is negative intercept, and then the parameter estimate for education is negative, indicating that there is negative association between education and hospital visit after controlling for age. And then we can also see here the multiple R squared value of 72.74. Let's do the second scenario where we treat this variable is categorical. To do that, I will just copy this code and then change the name to model 2, and then the outcome will be same. And then instead of education here, we will have to put the indicator variable that we just created. So our first let's consider our reference education level is education low, so we don't have to put that here. So we keep education medium is education medium, and then the second will be education high. So the estimates for these variables will be compared against the reference of education low, and then the age will be there, and the data it's same. So now let's run this model to run, and then let's see the summary. And here we can see that the intercept has even declined, -5, and then the parameter estimates for this education medium and education high are negative, and though not statistically significant. And then when we see the multiple R squared value, it has increased slightly to 73.55. Let me copy that also here. So we see that there is an increase in the R square value in the first model versus the second model. So this first model in which we treat the variable is continuous is the nested model, and the second variable that we ran with additional parameters and flexibility is the full model, right? So compared to the nested model, full model has a relatively higher R square value, and which also makes sense because there are additional parameters there. However, we do not know if this increase in the multiple R square value is significant, right? So how do we check that? So to do that, we can perform a partial F test. So to do that, we can use the ANOVA function in R, and then we do model 1 and model 2. So in this test, in the partial F test, the null hypothesis that we set is the nested model, the first model where we treated it, this education variable is a continuous variable, is enough. We don't need extra parameters. So the null hypothesis will be the nested model is enough, and for model fitting. And the alternate hypothesis is full model provides better model fit compared to the nested model. So when we run this ANOVA test, we have here in the result, you can see that there is the analysis of variance table, and here it specifies model 1 and model 2, and here we can see the statistics value of 0.184 and then the p-value. So the p-value here is 0.68, which is greater than 0.05, right? So if we set our level of significance as 0.05, then then the p-value here is greater than 0.05. So we fail to reject our null hypothesis. In other words, we can say that the additional parameters in the full model here are not helping that much in improving the model fit. Therefore, we can treat the education variable in this data as a continuous variable. Statistically, we can say that education can be treated as a continuous variable in our data. However, as a researcher, we should also always take into account what makes more sense in our case. what makes more sense for our data. That should also be included in guiding the decision around how to handle and how to treat the variables in the dataset. I hope you found this video useful. Thank you for watching.